Okay, we're going to talk about two more things as we finish limits. The limits unit, we're going to talk about the IVT, the intermediate value theorem, and we're going to talk about limits at infinity, which is really not that earth-shaking, but let's first focus on IVT, which is important. So I put up here the formal definition, which sounds a lot more complicated than it is, and I'm going to use an example right away of a cubic function here. And we'll illustrate it using this cubic function. So if f is a function that is continuous over the interval ab, now it's a closed interval, right? It's a closed interval. So let me show you what that would look like on our graph, right? So I'm going to pick an a of -1, actually. So we'll call that a, and we'll call b all the way up here 2. Right? So f of a. So ab is the x values, of course, right? So in our example, a equals 0. Actually, I said -1 before. I meant 0. And b equals, looks like 2. Yeah. Okay, so in our example, the interval is 0 to 2. Closed interval, includes 0 and clear it's 2. Okay, and k is some number between f of a and f of b. Now, f of a is the y value, of course, and f of b is the y value at b. So let's be clear about that, right? So in this case, f of a, as I have it drawn here, is equal to -1. And f of b is equal to 3, right? So x value 2, so this is the point 2, 3. And this is the point 0, -1. Okay, right? So it says, and k is some number between these two. So we've got a lot of choices for k, right? We're going from -1 to 3. So k could be 0, k could be 1. Of course, it could be a decimal too, but I'm just talking about some integers here to make it easy. Then there exists a number c between a and b, right? So between 0 and 2, such that f of c equals k. All right? So I'm going to pick a k, and that's typically how you have to deal with problems in this section. I'm going to pick a k, and of course my k is limited, right? Because k is some number between f of a and f of b, right? K is some number between f of a. So in our case, k is between -1, that's f of a, and 3, right? So the only integer one I think I have here is, actually it's not an integer one, but I'm going to pick this one of 0, right? I'm going to pick this one 0. So I'm going to pick a k of 0. Remember, k is a y value, right? Because k is some number between f of a and f of b. These are both y values, right? So from -1, ours is -1, and this is 3. So I'm going to pick my k value of 0. Okay. So there exists a number c. That's what we're looking for, right? Between a and b, such that f of c equals, in our case, 0. Right? So when does the function equal 0? Well, the function equals 0 right here. The function equals 0 right here. And this point is something like, I'm not really 100% sure, but it's something like 0 for y, of course. And x looks like it's, I think it's actually 1.6 exactly. 1.6, okay? So in our problem, this c is 1.6. Now, what this is saying is it's continuous, right? Because if it's discontinuous, that's not going to necessarily be true. It's a continuous function, which means if you're as low as -1, right? And let's make sure the interval is clear here too. So it's from there, right, all the way to here. So in this interval, right? So if you're as low, here it is. If you're as low as -1, so this is my border here, right? If you're as low as -1 and you go forward to the right and you get as high as 3, right? Somewhere in between here, you can pick any y value you want, and there has to be an x value, but that x value has to be between here and here, right? Between between 0 and 2, all right? And it works because our value is 1.6. Is 1.6 between 2 and 0? Yes, it is. So there has to be, and this is the key here. I'm going to really spend a lot of time talking about this. Oh, it actually doesn't say it here, but it should say there exists a number C between A and B, right? But it's really, it should say at least one value, at least one. Okay? Why? Well, because my function might be more complicated than this easy cubics, right? So if I had a function, and I'll make it different all the way around. So some weird function is coming from over here. It passes through. It has to have a y value of -1 and an x value of 0, okay? But it might do this, right? It might do this, and then it might continue like this one does to here. Well, sorry about that little piece at the end. So what happens? Well, actually, in this case, because we picked our k to be 0, right? We picked 0 here, so we're saying, look, if k is 0, there's got to be some number c. So our number was 1.6 before, but there's 2 other times in this weird blue function that I drew. There's 2 other times, right? So in this one, it's 0.8, comma 0, right? And in this one, I don't know what this is. I kind of missed an exact point here. Let's say it's 0.3, comma 0. Right? So in this case, there's 3 zeros of the function. So using purple here, right? There's actually 3. So I said before, at least one. It doesn't mean that there's only one. There could be 3, there could be 2, there could be 4, there could be plenty more, right? Depending on how much my function is wiggling around this point. So there are 3 places where the y value is 0. Remember, that's what k is, right? K, I should use purple there, but k is the y value. So there's 3, I used blue, so let's use blue. There's 3 places, right, where k is 0. So there are 3 c values. 1.6 was one of them now, 0.8, and 0.3 in this new example, right? C equals this, C equals this, C equals this, okay? So in this case, there were 3. So it's just, because it's continuous, because there's no sudden jump, right, it has to be like that. Another great example is if, let's say at 8 years old, right, at 8 years old, you're 4 feet tall, okay, and at 12 years old, you're 5 feet tall. If you pick a number between 4 and 5, right, so if you pick a number, you say, well, somewhere you've got to be, again, you're growing continuously, right? Somewhere there's got to be a number, so 4.2. There's got to be some year when you're going to be 4.2 feet tall, right? You can't not get to 4.2 feet. You can't skip 4.2 feet. And you're not going to shrink, most likely. You're not going to shrink below 4 feet. You're going to keep growing continuously to 5 feet. So somewhere, right, there must be a c value, right? There must be a c value here. This is your k value. So your y value is 4.2. There must be an x value between 8 and 12, right? Between 8 and 12. Between A and B, right? So between 8 and 12. And of course, it could be 10 years old. It could be 11 years old. It could be 9 years old. It could be 8 years and 6 months, whatever it is. But there has to be. Okay? So notice it doesn't have to be a 0. I picked 0 here because my graph had some nice, easy numbers at 0. I picked that for k, but k could be 4.2 feet. All right? And a more pertinent application or example would be velocity, right? So if your velocity, remember velocity includes direction. So if your velocity is positive, so let's say it's going north, so let's say it's positive 10 miles an hour, that's north. And then later on, your velocity is negative 20 miles per hour, which means you're going south 20 miles per hour. Well, somewhere in between these two, right, you must have stopped. If you're driving north at 10 miles an hour, right, you may not have stopped, you may have done a U-turn, but my point is your northerly direction, your direction, and your velocity must have been 0 at some point, right? So you must have hit a 0 in between here. And there has to be a time that's doing that. So if this time was at your starting time, and this was, let's say, an hour later. Somewhere between the 0 hour and the 1 hour, you must have stopped, right? You must have had a zero velocity, even if it was for a second. Okay, so they're going to ask you on the exam for IVT, they're going to say, how does this apply to some problem we're working on? Very likely it's a velocity problem or something where they're asking you, did it pass through this point? It may not be zero, but often it will be. All right, and then the last topic really quick is infinite limits. And infinite limits are a little confusing because they're really not real limits, and they're not real limits because infinity is not a real number. But all we're doing is we're differentiating how a limit fails, and we're specifically talking about limits failing when they're unbounded. So unbounded limits have more interest to us than other limits that just fail because there's a discontinuity. So the first function I have here, 1 over 1 minus x, looks like this. Put it in Desmos, you'll see that, okay? And we're going to talk about the limit when x approaches 1, of course, right? We're trying to make the denominator 0. That's how we're going to get this infinity. So we can't write this. We can't write the limit as x approaches 1 of, we'll call this f, right, to make it easy. So we can't say the limit as x approaches 1 of f, right, is equal to infinity. That's not true, okay? Because from the left side, it's infinity, but the right side, it's negative infinity. So I can't write this, but I can do this, right? Watch this small change here. I'll color code it. I can say from the left, right, the limit as x approaches 1 from the left of this function f is positive infinity. Okay, I'm getting closer and closer and closer to infinity. It's unbounded, really, right? We talked about that in the last video. And I can also say that the limit, I'll do it in red, of f as x approaches 1 from the right side is negative infinity. Okay? Remember, this is still not a real limit. So if somebody says, does this have a limit? You say, no, it doesn't have a limit. But it does approach infinity from the left, and it approaches negative infinity from the right. So that's important because that will, for example, in this case, and all these cases actually, let us know that there's a vertical asymptote. So if the limit goes towards infinity, I know that there's a VA at this point. So in this example, though, I can be specific about without the left and right. In other words, I can say the limit as x approaches 1, right? Here's my VA here. The limit as x approaches 1, we'll call this g of g, is equal to infinity because they're both approaching infinity from left and right. It's not wrong to put a plus here or a minus here and write it twice, right? So in other words, I can also write the limit as x approaches 1 from the left is infinity, and the limit as x approaches 1 from the right of g is infinity. These are both true, but it's much simpler just to simply write this. So for this problem, I would write this if someone asked me what's the limit considering infinite limits. Does it have an infinite limit? And these, though, I have to leave as two separate limits. Okay, same thing over here, right? So I think you're getting the hang of this. Let's call this h. So the limit as limit of h, as x approaches 1 from the left is going to equal negative infinity. But from the right, the limit of h as x approaches 1 from the right is going to equal infinity. I can't make a single limit statement like I can here. I've got to keep them separate. And then the last one, even though they're both negative infinity, so I can write it once. I don't have to write the left hand and the right hand. I can say the limit of I, the limit of function I as x approaches 1 is equal to negative infinity. I can write these two other limits. I can say right hand and left hand is also negative infinity, but I don't have to. I can write it in this easy statement. So they're still not real limits, but they are different from other limits that fail. Like, for example, when we had a jump, right? So when we had a jump like this at 1, we'll do it at 1. And we had a interval like this, a piecewise function like this, and we said, what is the limit as x, the limit of this function, we'll call this j, as x approaches 1 of j equals what? Right? It's dne. In other words, it doesn't exist. Okay, so this limit fails, but it's not an unbounded limit. It's not the left-hand limit is approaching some negative number here. The right-hand limit is approaching, let's say, 2 or something like that. But there's no limit at dne. And it's different from an infinite limit, or a limit that goes to infinity, because these tell us about vertical asymptotes. These really don't tell us much, other than there was a jump. All right? So these are infinite limits, but they're still not real limits.